Welcome to another problem solving session doing nodal analysis on circuits. Let's just jump right in. And so we got node 1, node 2, node 3, and node 4. We could just set this as the reference node, and then this is going to be V1, V2, and V3. We need a KCL equation, and remember the KCL equation was just Kirchhoff's current law. So KCL1, we could set that up to be 1 amp flowing into it plus IX flowing into it from this branch here. And that's a voltage, current dependent voltage source, and so it'll have an unknown current. And so then this is now the currents flowing out of node 1 are V1 over 4 ohms plus V1 minus V2 over 1. KCL2, we got V1 minus V2 over 1 plus 10 minus V2 over 2 is equal to 2VO, so this one here, plus V2 over 4. KCL3, 3 nodes, 3 equations, because we have 3 unknown voltages. And so now we got 2VO flowing into it, which is equal to V3 over 1 plus IX. Okay, and so for each evil branch, this is called an evil branch, wherever you just have a voltage source by itself, you could set it up so that obviously you could see from here V3 is just going to be V1 plus 4I naught. And then for this dependent voltage source, we need to figure out the thing that it's dependent on. We need another equation for that, and that's going to be IO, and IO is just IO is the branch current through here, and that is just going to be V2 over 4. And then another equation that we need is one for this dependent current source. We could also say VO is equal to V1 minus V2. Okay, and so now let's list our unknowns and our equations. So our unknowns, oh yeah, and then for this evil branch we also need one. So yeah, we got that. Okay, so we have V1, V2, and V3 as unknowns, and we have IO and VO as unknowns. So there's 5 unknowns. Oh wait, we have one more probably somewhere here. And IX, yes. So we have 6 unknowns and 6 equations. Plugging this into our graphing calculator or in a solver will give us our solutions. Alright, after plugging the equations into the graphing calculator, I got these values for V1, V2, and V3. Whenever solving these kinds of problems, it's always helpful to go back and just double check that your numbers that you got actually make sense. And so what we could do is we could just go back and make sure all the currents at one node actually sum up to whatever's on both sides of each other. And if they do, then you probably done it right. Let's start off with this circuit right here. So the main idea behind mesh analysis is to basically draw a bunch of loops, which we call meshes, and then assign loop currents or mesh currents to each one of those loops, and then using Kirchhoff's voltage law, KVL, or Kirchhoff's voltage law, we can go around it and we can go around the loop, and basically it states that the sum of all the voltage drops slash gains must be equal to 0, because hey, if we go around the loop, we have to end up being at the same potential that we started at. So for example, in this loop, we assign mesh current I1 to this left loop right here, and mesh current I2 to this loop right here. That's the first step. Assign mesh current. Okay, and now after that we have to use KVL. So we have to write voltage equations for each of these. So going around this loop over here, we can start at 10 volt rise across this, and of course it's going to be a voltage drop across the resistor if the side where the current enters into the resistor is going to be higher than the in potential relative to the side that where the current's exiting the resistor, because the resistor dissipates some of the energy, and which decreases the voltage. So there's going to be 4 times I1, and there's going to be a voltage gain across this one since we're going from negative to positive, so we're gaining potential. It's going to be plus 2Ix, and then minus 6 times apologies 6 times I1 minus I2. So these two currents are opposing each other in the resistor, and so adding up the sum of their drops is going to give us the actual net drop in the resistor. So because the net current is flowing in and flowing out, so this is I2 flowing in, I1 flowing out, and so Ix, which in this case is defined like that, is going to be I1 minus I2, because we're assuming I1 is positive, and there's going to be a positive voltage drop going from top to bottom. And so now this is all these drops are going to be equal to 0, and so that's our first KVL equation for the first loop. For the second loop, we'll go, so there's going to be negative 12 volt drop, and then minus 6 I2, that's the drop because of I2, and then the opposing current's going to be I1, and then you're going to have another drop because of this resistor here, because I2 is like that, it's flowing this way clockwise, and so there's going to be another drop there, and that's going to be equal to 0. Now we have 3 equations and 3 unknowns. We can just plug this into the graphing calculator and get our equation solved. Alright, after plugging it into the solving calculator, we got I1 is 0.8 amps, I2 is equal to negative 0.9 amps, and Ix is equal to 1.7 amps. And that makes sense because I2 is actually going in the opposite direction, and so when these two feed in this way, at this junction here, the only thing is that could happen is for them to add, so 0.8 plus 0.9, you get 1.7, and that's the current flowing through the top vertical branch in the middle. And that's that for that question. Alright, so this is the next problem, and so the first step is to write out all the meshes. So this is I1, that's our first mesh current, this is I2, this is I3. So we got 3 meshes, so we're going to have 3 different KVL equations, or Kirchhoff voltage law equations. And so let's start with the top branch. So the voltage drop across the first branch is going to be minus 10 I1 plus 6 volts, since we're going from negative to positive on the battery. We're going to have a voltage drain of 6 volts, and then we're going to have some voltage dropped across this 2 ohm resistor, but there's an opposing current I3, and so we have to account for that. So this becomes 6 minus 10 I1 minus 2 I1 minus I3 is equal to 0. And so now that's our first mesh current equation done. Now let's solve for I2 first. So this is going to be minus 6 volt drop minus 5 I2, and then there's going to be an 8 volt gain, and then minus 1 ohms times I2 minus I3 is equal to 0. That's the KVL for the second one. And finally for the third one, we can say there's minus 8 volt drop minus 4 I3 minus 2 I3 minus I1 minus 1 times I3 minus I2. So you have 3 unknowns and 3 equations, I1, I2, and I3. And we also have this current. We want to know the current through that branch. Let's call it IX. And so IX is just going to be I2 minus I3. So 4 equations, 4 unknowns. We'll just plug this into the HP prime graphing calculator, which can solve this system of equations for us. Alright, after plugging it into the graphing calculator, we got these values for the mesh currents and the current through this branch over here. And that's that for that problem. Alright, looking at this problem, we're gonna have 4 mesh currents, and so let's choose blue. We got 1 mesh current going through there, another mesh, and 1 more mesh. Let's call it I1, I2, I3, and I4. Okay? So now notice here there's a current source in between 2 meshes, and so that's going to cause some problems, but we'll deal with that later. Let's first do the KVL equations for these 2 meshes over here. So remember, the entire idea behind doing KVL is that the sum of all the voltage drops slash gains will be equal to 0, because when you get to the same point, obviously the voltage has to be the same. If the sum of the drops and the gains weren't that, then just math won't work, right? So let's do it for this one. Oh no, let's do it for I4 first. This loop. So we got a 30 volt gain because we're going in from this side and we're going up, so we're gaining 30 volts of electric potential relative to this side. And then we're gonna drop off, since the power is gonna be dissipated across the 2 ohm resistor, and so you got 2 times I4, but it's going to be opposed by whatever drop or gain that the other mesh current is going to cause, and so this is going to be the net drop of voltage across the 2 ohm resistor. And let me move this over here. And then this one here is going to be the same idea. So there's going to be some net drop of voltage across this one, because resistors dissipate energy when currents pass through them, because the internal structure of the resistor resists change and resists like current flowing through it. And so there's some type of, like, think about it like a tax. So when you want to push a certain amount of current through it, there's some voltage drop or some tax that the resistor takes, and so it absorbs some of the power in the circuit. That's how I kind of think about it. It's not completely true, but it works for me. So yeah. Okay, so this is the first Kirchhoff voltage loop that we did. And so now let's move on to I3. These are all drops, so I'm just gonna write them as a gain, right? So this is gonna be 6 I3 minus I2 plus 1 times I3. This one is only affected by this current I3, and then plus 3 ohms times I3 minus I4 is equal to 0. Alright, now let's deal with this current source here. We know that the 2 mesh currents have to add up to this independent current source in the center, and so what we get is I2 4 is equal to I2 minus I1. I'm assuming I2 is greater than I1 because obviously the 4 amp source is greater, and since these two are parallel to each other and they're in the same direction, I will give I2 the positive value where I1 is the negative value. And so now we just need one more loop current, but the thing is that we could also extend this and try like that. And so now we have to do the KVL on this larger loop, and the benefit of doing it this way is that now we don't have to deal with independent current source, and we could just do the loop as it is. So this is going to be 4 times I1 plus 8 times I2 plus 6 times I2 minus I3 plus 2 times I1 minus I4, and this is all going to be equal to 0. So now our unknowns are I1, I2, I3, and I4. And in the problem, we want to find the current here, so let's just call that IX. IX is literally just going to be equal to I4, so we don't really need an equation. So whatever we get for I4 is just going to be IX. So now we're going to solve this system of equations and solve for the 4 currents. Alright, after plugging it into the graphing calculator, these are the values that we get for the currents. And that basically solves the problem. Alright, so now this is the next question that we're going to be looking at. We want to find the current IO and the voltage drop across this 30 ohm resistor right here. So the first step in mesh analysis, like always, is to draw our meshes. So you got I1, that's the first mesh current, I2, and I3. Now, something to note out is that we can draw our mesh currents in any direction that we want. We can do clockwise or anti-clockwise because the principle still stays the same, and that the sum of all the voltage drops and gains around a closed loop will always be 0 because we're going to get to the same potential that we left at. Okay, with that in mind, now let's just write out the KVL equations, the Kirchhoff voltage loops or law. So we got 80 volts gain across this since we're going up, and then we got a voltage drop across this one since the current is flowing from left to right. So you got minus 20 I1, and then these two currents are going to be opposing them, so you have to account for the net gain in slash drop in voltage, and so that's going to be 30 ohms times I1 minus I3 is equal to 0. And then we need one more for this one, so this is going to be minus 20 I1 minus I2 is equal to 0. We have to write another Kirchhoff voltage loop. Let's call this Kirchhoff voltage loop 2. And so this is going to be another 80 volt gain, and then we're going to drop off 20, but it's opposed by I1, and then we're going to drop off 30, but that's opposed by I3, and then we're going to drop off 20 I2. That's 0. Now finally we're going to do it for this last loop. Since they're all drops, we're just going to write them out as a sum. So this is going to be 30 I3 minus I1 plus 30 I3 plus 30 I3 minus I2 is equal to 0. So IO is just going to be equal to I3, and V, the voltage drop across the 30 ohm resistor, is just going to be Ohm's law, so 30 times whatever I3 is. So now we're just going to plug this into our solver, and we're going to solve the system of equations to get our answer. Alright, after plugging it into the graphing calculator, this is what we got as our solution to our circuit.